Hi, today I'm going to start to talk about the equilibrium of the rigid body in 3D condition and how we can handle that. If you remember in 2D condition, when we need to find if there is a rigid body in equilibrium, we'll say that, okay, we'll find all sigma fx is equal to 0, sigma fy is equal to 0, and sigma m about any point should be 0. In other words, all the forces should cancel out and all the moments should cancel out. So we have three equations: sigma fx, sigma fy, and sigma f about any point. When we have a 3D object, we have the same thing, but most of the time we have to do it in the vector format. So in 3D format, when we want to see if the particle is in equilibrium, first of all, we have to have all the forces in vector format should be 0, and all the moment about any point in the vector format should be 0. So we have to satisfy these two equations. Remember, in 2D, most of the time we do all the calculation, almost all the time we do the calculation in a scalar. So it's just positive, negative, depend on which direction the force is applied, or positive, negative, depend on which direction the moment rotate. But here we will need to do that in a vector condition, except for some simple cases that you can do the scalar format, so you can do it also in 3D. But in most cases, you may not be able to do the scalar, so you have to do the calculation in this condition. Eventually, when if we write this equation, if we want to write this equation, it would be like that. Assume that we have the rigid body. So we write the equation, add them all together, and if sigma fx comes out as this, sigma f, sorry, if sigma f comes out as this, is fxi plus fy. So it will, let's say, the sigma f in vector format is going to be sigma fx I plus sigma fy j plus sigma f z k. And if we want to say this one is 0, we have to say that sigma fx should be 0, sigma fy should be 0, and sigma fz should be 0. The same for the moment. If we write the moment eventually is 0, and sigma m comes out that sigma mx I plus sigma my j plus sigma mz k is 0. So if we have something like that, so again we are going to have sigma mx is 0, sigma my is 0, and sigma mz is 0. In other words, we have very similar to what we have in 2D. So we have all the forces along the x-axis should be 0, all the forces along the y-axis should be 0, all the forces along the z-axis should be 0. The same, all the moment about x-axis should be 0, all the moment about y-axis should be 0, all the moment about z-axis should be 0, and that's how we do it in 3D for our calculation. So how we find if it's in equilibrium. Now let's a very simple example and show how it works. So assume I have an object that, so assume I have an object like that. So that there are three forces applying on that object. So I assume this is a force here, and a force here. I'll call them then F1, F2, and F3. And I have a point over here. If I have these three forces applying on that object and once I want to know if it's in equilibrium, so first I'm going to write all the forces as a vector. So F1 is going to be F1xi plus F2, F1 Fy1j plus Fyzk. The same for the F2. So F1, F2 is F2xi plus F2yj plus F2zk. F2zk. And for the F3 also, so I have F3xi plus F3yj plus F3zk. So I write all my forces in this format. So I have F1, F2, and F3. Now I have to say that, okay, what I need that is sigma fx is equal to 0. So I'm gonna just say that sigma f is equal to 0. So I'm gonna add all these forces. So it means that F1 plus F2 plus F3 is 0. So I have to add them all together. So I have to add these three together. So it's going to be this one, 1xi plus F1yj plus F1zk plus the second one, F2xi plus F2yj plus F2zk plus the third one, which is F3xi plus F3yj plus F3zk, and this should be 0. Now I expand it and then I put all the one with the I together. I put all the one with j together and put all the one with the z with the k together. So if I come here and says I would put all the one with the I, so it's going to be F1x plus F2x plus F3xi plus, now put all the with the j together, so Fy1 plus F2y plus F3yj, and then I will put all the one with the k together, so it's going to be F1z plus F2z plus F3z k, and then it's 0. Now if I want to say this one is 0, so I'm going to draw the line here. So if I want to say this is 0, so the I component should be 0, the j component should be 0, the z component should be 0. And in this case, when I write it like that, the I component, this I component, it is the sigma fx. The j component is sigma fy, and the z component, what I have here, is sigma fz. So when I say here, I said, okay, the I component is 0, it means that the sigma fx is 0. So sigma fx is 0, or otherwise the I component is 0. So f1x plus f2x plus f3x is 0. Then I have sigma fy is 0, which is going to be this component, which is going to be fy1 plus f2y plus f3y is 0. And then I have sigma fz is 0, which is going to be this part. It's going to be f1z plus f2z plus f3z. It's going to be 0. So I have three equations here, and I can use it to solve my problem. So these are the equations we get from the forces. We get from make the sigma F equal to 0. So we have these forces. If we add all the forces in a vector format, this is what we are going to get. The second set of equation we are going to get, depending if we need it, we are going to get or not, is the moment we are going to get from the is the equation we are going to get from the moment. So the first one was sigma F is equal 0. The second one is sigma M is 0. So I'm going to write the M1, M2, and M3. And if I want to write that, it's going to be, first of all, if I have it here, so this is going to be my, it's going to be R1, so it's going to be R3, this is going to be R2. So sigma F is going to be sigma M is going to be about any given point. So here I point about O. So if I want to write about point O, so I'm going to have the position vector goes from the point to the force, from the point to the force, from the point to the force is 0. So it's going to tell me what I'm going to have here is this R1 cross F1. So the moment for the first one, so M1 plus M2 plus M3. So the moment created from first force, the moment created from second force, the moment created by the third force will be 0. So therefore the moment created by first force R1 F1 plus the moment created from the second force is R2 cross F2, and the moment created by the third one is R3 times F3, and this should be 0 when we have it. And eventually when we write it, when we expand that, if we calculate R1, R2, R3, and we have F1, F2, and F3, if we calculate, for example, so as I said, so the F1, again, I'm going to say F1 is F1xi plus F2x, F1, sorry, F1yj plus F1zk. So this is F1. F2 is F2xi plus F2yj plus F2zk. And F3 is going to be F3xi plus F3yj plus F3zk. So these are the, and then we need to calculate the R1, R2, and R3. Also we have to have the R1 is R1xi plus R12j plus R1zk, and the R2 is R2xi plus R2yj plus R2zk, and the R3 is R3xi plus R3yj plus R3zk. And if we calculate this equation, so R1 F1 plus R2 F2 plus R3 F3 equal to 0. So we know that each of these one we can calculate it from the determinant. So the first determinant is I, J, K, and it's going to be R1x, R1y, R1z, and then the component of F1, F1x, F1y, F1z, and then plus this one again is going to be I, J, K, and the component of the R2, R2X, R2Y, R2Z, and the component of the F, which is going to F2X, F2Y, F2Z, and then the third determinant, again, I, J, K, and the whole thing is 0, so also the R3, so R3X, R3Y, R3Z, so the component of, and the component of the F3, F3X, F3Y, F3Z, and it's going to be, this eventually going to be 0 if we calculate. So if we look at that, this one is this determinant, and then the second one, the second term is the second determinant, and then the third term is the third determinant. So it's the third determinant. So each of these is one determinant. If we eventually, if we do the calculation and add them together, we will end up to having something like that. So sigma m about O is going to be sigma m x I plus sigma m y j plus sigma m z k. So if you expand that, eventually when you simplify it, you will get something like that. And if this is 0, then sigma m x should be 0, sigma m y should be 0, and sigma m z should be 0. In other words, the I component, the j component, and z component should be 0. And if you look at here again, it tells you all the moment about the x-axis should be 0, all the moment about the y-axis should be 0, all the moment about the z-axis should be 0. So it gives you three another equation. In total, we are gonna have 6 equations. So we have 3 equations: sigma x along sigma f along x should be 0. So sigma fx is 0. So all the force along the along the x should cancel each other. All the force along the y should cancel each other. All the force along the z. So sigma fx, sigma fy, and sigma fz is 0. So these are the force along each axis, and these three are moment about those three axes. So sigma moment about x-axis, moment about y-axis, and moment about z-axis should be 0. So total with the sigma fx is 0, sigma fy 0, and sigma z 0, it will give us 6 equations, so we can use it to find the unknown in our problem. Okay, let's look at an example, see how we do the equilibrium in 3D. Assume you have a plate, and it's placed sitting on the xy plane, and there's a force applied on this edge of that is 100 Newton, and there's a weight applied on that is 200 Newton. So these two forces apply on that, and it's held by 3 supports in A, B, and C. These three supports hold it in place. So we want to find the support reaction or reactive forces at A, B, and C for our calculation. One thing is, I'm gonna do that first of all is draw the free body diagram. So the free body diagram, this is like anyone, so just disconnect it from any other forces and draw that part. So I'm gonna draw that plate disconnected from any forces, and then I will put the forces on that. So I have the weight, this is going to be 200 Newton, and then I have 100 Newton applying on this edge, and then I have the reaction. Remember, when you want to put the reaction in the 3D, try to put the reaction in the direction of the axis. It helps you. If you find it's going to be negative, and after your calculation it comes out negative, then you know that your support is in the opposite direction of your axis. So here also I'm going to have for the A also I have the AZ, this reaction from the A, and the reaction for the B is going to have the three reaction. One of them is going to be, so I have a B X, which I'm going to put it in the X axis, so it's a B X, then I have B Z, and I'm going to have the BY. So the three reaction here, and at the C I have the CZ. So I have 1, 2, 3, 4, 5 unknown, and 2 forces apply on that, and then I want to find the these 5 unknown. So I will start to write the equation. So the very first thing I would write is the sigma fx is 0. If I write the sigma fx is 0, the only force I have in the fx direction is bx. So the only force is a bx. There's no other forces here, so I have bx, and it's going to be 0. So the bx is 0. If I write the sigma fy is 0, then the only force I have in the y direction is also by. So the by is going to become 0. There's no forces there. Now I want to find the other 3 unknowns. So I have bx, by. So I want to az, bz, and cz. I need to find these 3. And it's easier to go and find it, use the moment equation. The first moment equation I can write is that to see, we will choose to write the moment about the axis or point that eliminate most unknown. So here, if I write the moment about axis BC, if I write it about the axis BC, the CZ and BZ would be all of them, because they are on that axis, so their moment is 0. The only one has the moment, the unknown is the AZ, so eventually I can calculate the AZ. So I write the moment about BC, and I say it should be 0. So the moment about BC, if you or let's make it CB, so it's going to be in the direction of the y-axis. So CB, so about the CB. So if I want to write it about the CB, I will start with 100 Newton. So that's 100 Newton, and it rotated in a positive direction of the CB. It rotated like that, so my thumb is in positive CB. So it's a positive 100, and the distance is 3. The normal distance from the point to the CB is 3. Then I will look at the 200. Again, 200 respect to CB is positive, because if it rotated like that respect to CB, and then my thumb shows the positive, so it's going to be 200 times 1.5, and then I have the AZ, which is respect to CB is going to rotate it in a negative direction. So if my respect to CB is rotated like that, so my thumb is toward the board, so it's going to be negative AZ, and times 3. Again, this distance of the AZ to distance of A to axis CB is just 3. It's going to be 0, and then it will tell me the AZ is 200 Newton. For the next one, to find the next unknown, I'm going to find, I write the M respect to y is 0, respect to y-axis is 0. If I write it for the y-axis, see what forces I have. So again, I have this 100 Newton. So this 100 Newton, and if about the y-axis is going to rotate it in the positive direction of the y-axis, so it's rotated like that. My thumb is in positive direction, so it's a positive 100, and the distance is 1 respect to the y-axis. So then the force is the weight is 200, and again it rotated like that, and my thumb is going in the positive direction of y, so it's going positive. So it's got 200, and the distance is again the same as 1. And if you look at that, then we have the AZ, which is, if you look at it, the AZ rotated like that, and my thumb is going to be negative direction of y, so it's going to be negative, so it's going to be negative AZ times the distance from here to y-axis is 2. And then for the BZ is also, it's going to be negative, is rotating it like that about y, so it's going to rotate, and my thumb is going to, so the B hold it up, assume it's fixed at the y, so it rotated like that about the y, and my thumb is going, the right hand rule, my thumb goes against the y-axis, so it's going to again negative, and the BZ and the distance is 2, the same, the distance is 2, so the is 0, so the BZ would be negative 15 Newton. And the last one, we want to find the last one, we write the sigma F y is 0, because we already know all the forces except the CZ. So if we write the we have the AZ is a positive, there's a BZ plus the CZ minus 200 minus 100 is 0. AZ, BZ, CZ, all of them we assume is upward, so if we substitute in them, so it's going to be AZ is 200, BZ is a negative 50, plus CZ minus 200 minus 100 is 0, then CZ is going to come out negative 150 Newton. And since then it comes out BZ and CZ comes out negative, it means that they have the direction opposite of what we assumed, and the other one, the AZ, comes out positive, so it's the direction we assume is right, and the BX and BY comes out 0, so the direction does not matter anymore. So although this is the 3D equation, the 3D object, but we can solve it like the scalar, because we can find all the forces and the moment about the axis using the scalar notation, and do that. So if we can do that, it's the easiest way. We don't need to do that. Although because it's 3D, we can use the vector format, sigma F equal to 0, sigma M equal to 0 in the vector format. But because we can't do it in the scalar format, it's just most of the time easier to do that like that. If you cannot do that as a scalar calculation, then we probably need to do write all the forces and the distances as a vector, and do all the calculation in a vector format. Okay, next let's look at another example. Here we have the 3D object. We have a rod between point A and point B. So point A is in the XZ plane, and it has an X of 1 and a Z of 3, and B is in the YZ plane. It has a Y of 4 and it has a Z of 1. And at the center point here, at point C, which is the center of A and B, there's a force that goes from the center point of that rod toward the origin of the axis, so origin of the system here to O. And now we want to find the reaction forces at the A and B. Find this how much forces each of those supports is gonna have. So again, when we have this 3D object, the very first thing we need to do is just draw the free body diagram. So draw the free body diagram like that, and we have in this free body diagram we have this 100 Newton, and here at the A we have 3 AX, AY, and AZ that hold that end in its location, doesn't let it move. So there are 3 support forces, and we draw them in the X, Y, and Z, positive X and Y, Z direction. Remember again, in the 3D, especially in 3D, when you want to when you want to draw the free body diagram, which means that you remove all the connection from the body and then put all the external forces on that. When we want to do that, is that we remove that, we put all the external forces, but for the unknown external forces, try to put those unknown external forces, such as the forces at support A and B, in direction of the X, Y, and Z direction. So later on, if they comes out negatives, you know that they are in negative direction of what you assumed. So I'm gonna assume I have a support AX, so it's a reaction AX, and then I have reaction AY, and then I have reaction AZ for point A, and for point B, the same here. I have a reaction BY, I have reaction BZ, and I have a reaction BX. So this is my free body diagram. So I have all the external force. I first disconnect the part from any connection, and then I add all the external forces. So all the external forces, one of them is the active forces, that 100 Newton, that is pulling it down, and then there's the two supports here that holding in place. So in this, both A and B let the part rotate, so it doesn't put any restriction in the rotation. So we don't have any moment at point A and point B, but they don't let it move. So we have the restriction in the motion of in the X, Y, and Z direction, both in A and in B. So we have 3 components in A and 3 components of unknown in B. Now, if you look at that, we want to solve that problem. So we have 3 unknown, and it's the 3D problem. So we have to do it in vector format. First, I'm going to write the position of, so we know that the location of point we have is 0, 0, 0 for point O. For point A, for point A is X is 1, is Y is 0, and the Z is 3. For point B, it's going to be, its X is 0, Y is 4, and Z is 1. And point C is sitting between point A and B. And if you have a midpoint, you want to find a midpoint, you just add X together divided by 2, add Y together divided by 2, add Z together divided by 2. In other words, the C is just, if you want to write a C, is just C is just A plus B divided by, because the problem told us C is between A and B, so it's a midpoint. So it's going to be 0.5, 1 plus 0 divided by 2, 4 plus 0 divided by 2 is 2, and 1 plus 3 is 4 divided by 2 is 2. So that's the, that's the coordinate of C. So we add the X coordinate of A and B divided by 2, Y coordinate of A and B, and Z coordinate A and B, and divide by 2. So this is how we're going to get the midpoint C. So we have A, B, and C, these 3 points. And solve that. For the forces, now we are going to write everything we have in the vector format. So we start with the forces. So forces we have is forces at A. So the A is, we don't know any of its components. And we can, so we just write it as its component, AXI plus AYJ plus AZK, because we don't know any component. The same for the B. For the B is BXI plus BYJ plus BZK. So for these two, we don't know. For the F, we can find this. So if you remember the force, F is the magnitude of force times the times the unit vector. So unit vector here. So the force, let's say, is going to from C to O. So the unit vector of CO, and we know the unit vector of CO. The unit vector of, because it goes from C to O, the unit vector of the CO is the position vector that goes from C to O divided by magnitude of the position vector goes from C to O. So we'll start with RCO. The position vector goes from C to O, and it's going to be XO minus XC I plus YO minus YC J plus ZO minus ZCK. So then the RCO is, if we go there, X O minus C Y O minus Y C and Z O minus ZC is gonna gives us negative 0.5 I, negative 2 J, and negative 2 K. So it gives us, so this is going to be our value. So the unit vector in that case is going to be, the unit vector CO is RCO divided by its magnitude, which is going to be negative 0.5 I, negative 2 J, negative 2 K, and divided by its magnitude, which is going to be negative 0.5 squared plus negative 2 squared plus negative 2 squared. And it tells us is the UCO would be, if we do that calculation, it goes negative 1.74 I, negative 0.696 J, and negative again 0.696 K. So now we can't find the force, so the force is F UCO, and the F is 100 times the UCO, which is going to be I minus 0.696 J minus 696 K. So if we find that, so F is going to be 17.4 I plus, sorry, negative, so minus 69.6 J minus 69.6 K. So this is the F. I'm going to write the F down here. So the F is negative 17.4 I, negative 69.6 J, and negative 69.6 K. So these are the forces I have. Now that I have forces, I can say that all the forces in a vector format should become 0. So I'm going to start to write it here. So I know that sigma F should be 0. So here what I have is means that A plus B plus F, which is that this, if we consider this is the F, this should be 0. So if you add them as a vector, this should be 0. So we have them here. So we have them a x I plus a y j plus a z k. So this is the vector A. Then the vector B, which is bxi plus byj plus bzk, and this is the vector K. And then we have the vector F, which is negative 17.4 I, negative 69.6 J, negative 69.6 K. and this is going to be 0. Now I'm going to write all the I component together, all the j component together, and all the z component together. So first all the I components, so it's going to be ax, then I have a bx, and then I have negative 17.4. That's I. Then I will write all the j component together. So ay plus by minus 69.6, and the k component. And then I write all the, j component. And then I will write all the k component together. So it's j, and then I have az plus bz minus 69.6, k is 0. So if you remember, I said that all the x, all the component of x is going to, this one is going to be sigma fx. All the component of the j is sigma fy, and this is going to be sigma fz. So when we put that and said this is going to be 0, it means that all the component of I should be 0, all the component of the j should be 0, all the component of the k should be 0. So in other words, sigma fx is 0. It means that ax plus bx minus 17.4 is 0. Then I have sigma fy is 0, means that ay plus by minus 69.6 is 0. And then I have sigma fz is 0. It means that az plus bz minus 69.6 is 0. So here I have 3 equations, and I have 6 unknown. So it's going to be equation 1, it's going to be equation 2, it's going to be equation 3. So I have 3 equations, and still I have 6 unknowns. So it's not enough, but there are 3 equations. I need 3 more equations because I have 6 unknowns to solve this problem. So I need to find out 3 more equations for my purpose. We already use this equation, sigma f equal to 0. The other equation we have is sigma m is equal to 0. So we write the moment and just find another equation. So I'm gonna start to write it here. So I'm going to write a sigma m is equal to 0. But I have to either write it about, I have to write all the moment about one point. Here we can write it about point A, or we can write it about point O, or here I'm going to write it about point O, but we can write it about point A or B or any other point. If we write it about point A, the good thing is that these 3 will be cancelled out because they don't have any moment, and all these 3 force unknown would remain in our equation. So it gives us 3 equations with 3 unknown. If I write it about point B, the same, because these 3 would be eliminated from the equation, only these 3 remain in the equation. So I have 3 unknown, 3 equations, 3 unknown, so I can calculate these 3 from there. But here I just write it about point O in more general case, but we can later on try to write it from about point A or B or C or any other point, and you see the result will become out exactly the same. So I write them about point O. So if I write the point O, then I'm gonna have for the first one is I have for the point A. So I have a ROA, the position vector, times A, product A. and then I have the ROB, the position vector, times force B, and then I have the ROC times F. This should be 0. So if you look at here, I'm writing the, so for the forces I have there, I have one force at point A, so I have this is the ROA, and then I have forces at B, so it's the ROB, and then I have forces at C, it's the ROC. The thing is that if you look at the point, the force F, it goes through the point that I'm calculating moment about that force, because it goes through that force, it goes through that point, so its moment is 0. So we already know that this term is 0 because the force goes through the point O. Because the force goes through the point O, it doesn't produce any moment, so this one is 0. We already know that. So we have to find ROA and ROB and this calculation. So for ROA is XA minus XO plus so I plus YA minus YOJ plus ZA minus ZOK. So the ROA is going to be, so it's going to be 1I plus 0J plus 3K. So that's ROA, and then we need to find ROB, because we have ROA and ROB. So we have ROB, which is going to again be XB minus XOI plus YB minus YOJ plus ZB minus ZOK. And if we put them, so ROB, it's going to be 0I plus 4J plus 1K. So 0I, 4J and 1K. So these are the two we have. So now we want to have the sigma m is equal to 0. So sigma m is equal to 0. Therefore ROA cross A plus ROB cross B is 0. So ROA is this one, so it's going to 1I plus 0J plus 3K, and the A is going to be this, so it's going to be cross AXI plus AYJ plus AZK, and the ROB is 0I plus 4J plus 1K cross, and the B is BXI plus BYJ plus BZK, and this is going to be 0. So we have two cross product to calculate that. And if you remember, so I'm going to just write the ROA here. So like ROA is 1I plus 0J plus 3K, and ROB is 0I plus 4J plus 1K. Okay. So we are going to calculate these two, and you remember these two, we can write it as a determinant. So we have that is going to be as the determinant of the first set, which is going to be I, J, K, and then the component of the ROA. So the component of the ROA is 103. So 103, and the component then is going to be component of the A, which is going to be AX, AY, AZ. AX, AY, AZ, plus then go for the second one, ROB times V. So again we have the I, J, and K, and then the component of ROB, which is 0, 4, 1. 0, 4, 1, and the component of the B, which is going to be BX, BY, and BZ. So this is going to be 0. So to explain it one more time, how we get from here to there, is just remember that the moment was calculated by position vector cross the force, and we know that we can calculate the moment by using the determinants. Was the position vector cross the force, and that position vector cross force can calculate from the determinant. So this term ROA times A is IJK, and then the second row is the component of the ROA, which is 1, 0, and 3. So 1, 0, and 3, and then the third row is the component of the A, so it's the AX, AY, and Z. AX, AY, and Z. The same here, ROB times B. ROB cross B is just the first row is IJK. The second row is the component of ROB, which is 0, 4, 1, 0, 4, 1, and then the third row is a component of B, which is BX, BY, BZ, and BX, BY, BZ. And now if you expand this and calculate this determinant, remember we start from the I. We said, okay, we eliminate the row and the column that the I is in there, so it's going to say, and then add times it. So 1 AZ, so 1 times AZ, so 1 times AZ minus, sorry, eliminate that one. So we eliminate that one, so it's 0 AZ, so it's a 0 times AZ minus 3 AY I, and the second one is negative, so we start to eliminate row and the column. The J is in that, so it's a 1 AZ, 1 times AZ, so it's a 1 AZ, 1 AZ minus 3 AX, minus 3 AX, J, and then again plus, so we eliminate the row and the column. The K is in that, so it's going to be 1 AZ, again 1 AZ, sorry, 1 AY, so it's going to eliminate that, so it's going to be 1 AY, 1 AY minus 0 times AX, it's going to be K, and then we start with the second determinant, so plus, so eliminate the row and column. The I is in there, so it's a 4BZ, 4BZ minus 1BY I, and then we eliminate first the column, the row and the column. The J is in there, so it's a 0BZ, and the negative is 0 times BZ minus 1BX J, and then the third one is plus, and eliminate the row and the column. The K is in there, so it's going to be 0 BY, 0 BY minus 4BX minus 4BX k is 0, and let me see if I have them all right. So az, ay, 1az, 3ax, 1ay, 0, 4bz minus by. So yeah, that's right. Now I'm gonna just write all the so now I'm gonna write all the I component together, all the j component together, all the k component together. So if I start from here and write all the I component together, so I would have the negative 3ay plus 4bz minus by I plus negative az plus 3ax plus 3 plus bx j and plus ay minus 4bx k is going to be 0. So basically what we have here is the sigma m in a vector format is 0. So this first, the I component, as I said before, that the I component is sigma mx, the j component is sigma my, and this is the sigma mz. So the I component show the I component shows the sigma m. So sigma m about the x axis, it shows the sigma m about the y axis, and it shows the sigma x about the z axis. And then we have the sigma m about the x is 0. So then negative 3ay plus 4bz minus by is 0. Then we have the sigma m y is 0. So it's going to be negative az plus 3ax plus bx is 0. And then we have sigma m z is 0. Then we have ay minus 4bx is 0. And it gives us the three more equations. So this is going to be the equation 4, equation 5, and the equation 6. So we have 6 equations. Three of them is sigma f x is 0, sigma f y is 0, sigma f z 0, and here we have sigma m x 0, sigma m y 0, and sigma m z 0. So we total we have 6 equations. So if we solve this equation simultaneously, we will get the result. More about this equation. So if you look at that, this is the moment about the x-axis. So if you go there and look at here about the x-axis on the ay, which is going to be this one, ay has a moment in point A, and the reason it has the ax is parallel to x, so it doesn't have any moment. The az intersect with the x, again doesn't produce any moment. Remember, if the force is parallel or intersect axis, it doesn't produce any moment about that axis. So the only one that produces is ay, and the ay, its distance to x is 3, and if you look at that, it rotated, and my thumbs is going to be toward the board, so it's negative, so it's got a negative 3 ay. For point B, if I look at the point B, the moment point B produce about axis x, so we have the bx is parallel to the x, so it doesn't produce any moment, and then we have the by and bz, both of them produce the moment. And if you look at it, the by is 1, the by is the distance is 1, and again when it rotates, it's my thumb is going to be against the x, in the opposite direction of the x, or in the negative direction of x. So going to be negative by, and for the bz, if you look at here, the bz rotate like that, so it's going to be, my thumb is positive, and the distance is going to have is 4, so it's going to 4 bz. So we can write the same for y and the same for the z-axis, and you see each of them is like that. So although we write them all as a vector, eventually we get to these 3 moments about x, y, and z-axis. If you feel comfortable, you can do that from the beginning. So you can from the beginning write all the moments about x-axis, y-axis, and z-axis, and add them together. So eventually, if we add these 6 equations, 3 from the forces and 3 from the moment, we'll get the value for, so we get the AX is 8.7 Newton, and the AY is 34.9, and the AZ is 34.9. The same for the BX is 8.7, BY is 34.9, and BZ is 34.9 Newton. So get all these equations. Remember, in this problem, I wrote the moment about point O, so we can't write sigma m about point A, about point B, about point C, about any point we want, and then eventually we get a very similar equation, and then we can do that. So I here to look more general, I go for A, but if I write the sigma m about point A, so AZ, AY, and AX will be we eliminated because all of them go through point A, so only BZ, BX, and BY will remain. So I will have 3 equations, 3 unknowns, so I can calculate these 3. The same, if I write the moment about point B, the moment of these 3 forces will be eliminated because all of them go through that forces, and the only forces, unknown forces that they have for a moment about point B are A, X, Y, and Z. So again, I have 3 equations, mx is 0, my is 0, mz is 0, and I have 3 unknowns, so I could have solved these 3 directly from that equation. So remember, you can choose other points, so probably for this equation it would be easier to go for point B or point A, right, a moment about one of those points in case of solving it. But it doesn't matter which point you use. The point, if you write the equation correctly, any point you choose, eventually you get the same result in this case. So again, if you have a 3D problem, if you can do it in a scalar format, so do it in a scalar format. Otherwise, you have to write these 2 equations. I write them once more again. So sigma f as a vector is 0, and sigma m as a vector is 0, and then it gives us 6 equations, and depending on how many unknown we have, we can solve them to get our unknown in our problem.